Hello again, YouTube. Sorry for the slight break in on the channel. I've kind of been distracted doing other things, but I'm back for the minute. So I left this and I said I might clean up this Morse module that I created. I mean, it's a very simple thing just to demonstrate lighting LEDs on the cinnamon bun device, but then it became a mechanism for showing the difference between asynchronous and synchronous function. But I did say that I might clean up this API because I wasn't quite happy and didn't want to leave it in this state, and I'm going to try and do that now. And I think it's worth talking about just because this is, I've said it's a bad API, but why is it a bad API? It actually enforces a policy on the application. Now, in our case, the application is just this body of code, the main, which uses the Morse module to transmit the word "the," and that's the only API call that we have. So the policy is enforced that you can only transmit "the." Any other word you can't transmit, and that might be a valid policy for certain applications. It's a very this makes it a very application specific module. So if another piece of application code wanted to write the word "quick" or transmit the word "quick" using Morse, this module is no good. So we want something that's not application. We want an API which is not application specific and is more general. Look, it provides a mechanism to transmit characters, but it doesn't enforce any policy. So I really want to change the API to be something like we take a more general transmit function that just transmits a C null terminated string. So this application that we have here wants to transmit the word "the," so it would now just call the function with a null terminated string in C. It's as simple as that. But another application that wanted to transmit the word "quick" can do that. Like, we're not enforcing any kind of policy. The API, the Morse module is providing a mechanism, not enforcing policy. So we could actually change this to be, it can transmit the quick brown fox, and that's our API. Our Morse API, that Morse module doesn't enforce any kind of policy. It just provides the mechanism, so this is quite happy to do that. Now I've also defined here an init. Well, I haven't. I've nearly defined it, but I would normally have an init for a module. And I would document here, well, I'll document it at a later date, but you would document that the actual initialization of the Morse module should take place before you call an API function. So just to get into that, and so then, having said that, our main has to call that initialization function before it calls the actual API function that it wants to do the transmission. So I did this with, or I messed about with various configurations in the MPLAB X IDE, so I might actually create another one and call it, I might call it "good" for want of a better word. I can't think of anything just at the minute that's, I might think of something at a later date. For the minute, we'll just call this configuration "good," and we will, first of all, we'll remove this synchronous file from this configuration, and we'll add a new source file, a new C, and I've updated to MPLAB X 4.0, and this now is letting me create C files, so all good. And our C file, we want to implement these two API functions. And having done that, if we give this a name, this parameter, message, then that should actually be quite happy to build. So now we looked at Morse, an asynchronous version and a synchronous version. The synchronous version held up the processor because it had to finish before what it was doing before it returned from the function call. In the asynchronous, it just loaded up a buffer. But because we knew we were transmitting three letters, THE, our buffer was a fixed size, and I don't know if I actually made it 20, but yeah, it could have been a fixed size of 3 because we were only using 3 letters. Ordinarily, in this kind of situation, you would use what's called a circular buffer. And I don't know what level people are at who are watching this, so I've no what's the word, idea what level people are at. I'll just explain what a circular buffer is quite quickly. So a circular buffer, it mentally, we represent it like this. So this buffer just goes the whole way around like this. And we have an index here which points into this buffer, which is the right index. And we've also got another pointer. It's just an index into an array, and this is the read index. So in this case, our circular buffer will contain the characters that we want to store in the buffer. So the right index, we talk about producers and consumers of data, and they're both working at different frequencies or different rates. So in this case, our producer of data is our application, which is trying to print or trying to transmit the Morse for THE. So every time we write a character, we move to the next, we move that index on, and the producer comes in and wants to write another character, we put it into this slot and then move into the next slot, and so on. And the right index travels around this buffer like this. Now the consumer of data is the read, and it goes exactly the same way. It goes round the buffer, chasing. So in this case, when the consumer of data wants to read a character, is ready to take another character, it takes the character out of this read buffer and then increments it, points at the H. And the next time it wants to create a character, it takes the H and increments again. So everything's going around the buffer. And usually we'd implement this in C in a fixed size array. Now we can tune that array size at compile time. So I mean, if it was an array of I think that's about 10. So if we've an array of 10 characters, while we visualize it as a circular and we're implementing a circular buffer, it's actually implemented in a fixed size array, but we can change that array size at compile time. So this is index 0, and this will be index 9, I think, if I've done this right. Yeah, I've got that about right. So we start off with the right index there and the read index there. And the actual contents of this buffer, we're fixing it at compile time so that it's an array. So at compile time we decide what size we're going to make it. We can tune that later and recompile it and make it twice the size if we find that our producer is producing data at a rate that's too fast or whatever. And if the consumer is actually quicker than the producer, then we can reduce it in size. But we do that at compile time. But the actual contents of this buffer can expand and contract. So if there's a burst and we fill in THE space, the buffer becomes quite full. And then if the read, the consumer of data catches up, then it becomes empty. So when the read index is equal to the write index, it's empty. When the read index is, or when the write index is one behind, so if I change color to something like that, if the read index is there, and write index is there, then the buffer's full. But remember, as well as that it's worth noting that in this case, if the read index is here, so read is pointing at index 0 and write index is here, so write, then that's full. So it doesn't look like that satisfies this equation that it's full when read minus 1 is equal to write, but that's the case because of the size of the buffer. It's to do with it's kind of like clock maths that you'd use in encryption algorithms. So that's what we want to implement. We want to have a natural array. We want to implement this in an array of fixed size at a compile time that we can change later on, and we want a read index and a write index. Now we can, sometimes people would keep a count of the number of elements in the buffer as well, because it just simplifies some of the language that's used in terms of C language. But we'll see that now when I do this. So we need a transmit buffer. We're making it an array, and we'll call it, or we'll make it, let's see what it is. It's transmit buffer size, and we'll hash define that to be and the diagram I just drew, like 10 characters, so we'll call it 10 characters for the minute. Like I say, we can compile that we can change that at compile time, and tune that to whatever we want it to be. So we transmit buffer, and we want to read and write, and we want to read index. Now we could keep sorry, there's a semicolon that shouldn't be there. We could keep a track of the count as well, but we'll just use the equation there, or that when the transmit buffer is just when the transmit index, or the write index, sorry, is right behind the read index, then buffer is full. We'll need a standard int for that, uint16, which I like to use. So that's our buffer, and we're doing nothing with it. It's going to moan that we're not actually using variables, so It's just a warning on that. So we'll now, in our transmit function, we saw in the asynchronous version, like I say, that we just loaded up this buffer. So we're going to load up the buffer with the pointers, or with the characters. So we'll just create a local variable, and it's a pointer, and we'll make it equal to the message, and just use that, and loop round this pointer, taking characters and putting it into the message buffer. So we would say that the transmit message buffer at the message buffer write index is equal to the character, and then move to the next character. And of course we want to now increment that, so the transmit buffer and the write index, I'll do this longhand, is incremented and we want to take care of the case when it gets to the end of the actual circular buffer, and we can do that with just a modulus operator. So in this case, when the transmit buffer size is 10, we're going to loop around 0, 1, 2, 3. It gets to 9, increments, and it gets to 10, and 10 modulus 10 is 0. You could also do this in an if statement, but generally people would use a modulus operator. And that's a really bad implementation, but because we're not checking anything, so we should check here that for the start we want to check that the buffer isn't full. So if, now I've said if the write index plus 1 is equal to the read index, then it's full. So we want to say if it's not equal to, if it's not full, then we want to carry on and do these 2 lines. But we can't just do this simple plus 1 here because of the circular buffer, and we've already seen that we need the modulus operator. So we want to modulus that by and that's, I hope that's right. It may, so we want to check that the buffer's not full, and as you can see, that piece of that line of code is it's kind of not clear and readable in terms of what it's doing. So some people would actually store a count variable, and it's much easier to say if count is equal to Morse TX buffer size, and it could be quite clear then what you're trying to do, as opposed to doing modulus operators, increment operators, and then checking equality operators in one line. So I suppose count is more readable. And yeah, we could, I'll throw it in here. So yeah, I suppose that's more readable, and people would use that as an alternative to the actual the kind of long-winded version of doing it. We obviously have to then increment the count every time we add a message or a character into that circular buffer, and everything's happy with that. The other thing we should check is that the actual character that we're trying to transmit is a valid character. So what is a valid character? So if, I suppose first off, if it's a space, we'll be happy with that. Or if it's greater than or equal to the lowercase a and less than or equal to lowercase z, we'll call that for the minute the valid characters. Now that doesn't include the digits 0 to 9, so that's another, we can add that at a later date, but for the minute let's just do letters, and we'll add to it later. But yeah, we'll assume that those are valid characters. Now given that we've added that line, this is a bug that we're incrementing the pointer here, because if somebody puts a percentage sign into a text string, we'll actually check that the pointer is valid and it's not valid. So then we'll go pop out, we won't execute this, we won't execute these 3 lines, and we'll just pop back up and check the pointer again, and we'll check the percentage sign again because we haven't incremented the pointer. So at the end of this, after this if, we should increment the pointer and not in this assignment operator. So that then, for the minute, is our producer and consumer interfacing via an API which uses a circular buffer. And I think I'll leave it there because I don't want to get too, I could very easily get into an hour-long video if we go into the next steps. So I'll leave it there for the minute. Thanks a million for watching.